Our story gets slightly less nice, but still okay. In that we no longer have global existence uniqueness, but we do know that at least for some very small neighborhood, usually you can think of there being exactly one derivative with a zero coefficient. I'll come back in a second. Then in some neighborhood of the initial starting point, you have existence, but you don't know anything more than that. So you still have some existence, but not global anymore. You lost a little bit. And same thing with uniqueness and regularity. Now the model equation for parabolic PDE is the heat equation, which says that the derivative of a function in time is proportional to his Laplacian. Right? And this equation is governing how heat diffuses over a domain. Why does that make sense? Well, let's draw a little picture to find out. So let's say that here's A and B, and here's the distribution of heat, right? So here the Laplacian is going to be negative, right? Because this thing is pointing down, Laplacian is the second derivative. Yeah? So what this is saying is that over time, f wants to decrease, right? Similarly, if f were pointing this way, Laplacian is positive and wants to increase. Yeah? So the heat equation just kind of says that heat wants to, balance out over time. It wants to get rid of this curvature and make a nice flat line. And as you can imagine, the heat equation is a very stable equation. That as time goes to infinity, heat diffuses as a constant, or in fact, in general, it diffuses to a solution of the Dirichlet equation. You can see that, right? Because as time goes to infinity, if this thing diffuses indefinitely, then eventually S sub t is going to equal 0. Yeah, and that's the Laplace equation. All right. So anyway, what do you need for boundary conditions for the heat equation? Well, I'd better tell you what the heat looks like at time 0. Yeah, so just the heat everywhere on the domain. And then as time progresses, you need to tell me what happens on the boundary of your domain. Am I attaching omega to a refrigerator, right? In that case, I might be pushing heat into omega, or perhaps I'm just letting it diffuse out nicely, and so on, right? Those are Dirichlet and normal conditions. Our final example of a PDE that we care about is a hyperbolic one. The model equation for that is the wave equation. And all I do to get the wave equation with the heat equation is stick a second derivative in t. What do you notice? FTT has a plus 1 next to it, and all the spatial derivative have a minus next to it, right? So this matrix is indefinite. Now, unfortunately for us, even though this matrix is indefinite, this is an equation we want to solve, right? Almost all interesting PDEs are hyperbolic. For example, the wave equation, the Navier-Stokes, anything where fluids are sloshing around, right? I can let a fluid slosh around forever, and it might never settle down, at least in the absence of friction. Right? It'll just a wave can just keep propagating back and forth, back and forth. Obviously this is in theory. And because of that, right, this is a very difficult PDE to solve. Right? This is sort of similar to our time-stepping story, right? If I used backward Euler on the heat equation, that's kind of not a big deal, because backward Euler damps out motion, and the heat equation was all about like diffusion and slow movement anyway. If I use backward Euler on a hyperbolic PDE, then I'm slowly removing energy from my system, and eventually it's just going to dampen out and get boring, even if my fluid's supposed to be sloshing every which way. Yeah? So these equations take very careful simulation to do properly. And one of the boundary conditions are very similar to the heat equation. Right now I have to give you what the wave looks like at time 0. I also have to tell you the initial velocity of the wave at time 0. Other than that, it's the same. Okay. So, I'm not sure we're going to get to the end of this today, but that's okay. So, I'm trying to introduce PDEs sort of by analogy to the linear algebra that we've already seen. And in fact, the methods for discretizing PDE more or less carry this to completion. Yeah? So in particular, we can think of this d over dx operator, right? This thing that takes derivatives of functions, right? Takes in a function, gives you back the derivative of the function. We can think of this as sort of acting like a matrix. Now why is that? Let's say that I have two functions f and g, and I linearly combine them. AF plus BG. That's the same as linearly combining the derivatives, right? So in fact, pardon, this d over dx thing looks kind of like a matrix, right? Like that is, d over dx is to functions as matrices are to vectors, if we're doing this SAT style. Yeah? So here's how to carry this out. Now remember from about 4 weeks ago, so let's say I'm trying to discretize the second derivative of a function. So remember from about 4 weeks ago, we had an approximation. This is the central differencing thing, right? Or what did I do? Well, To approximate f prime prime at least to big O h, I put a 2 next to f at the center, and a minus 2, and I added the neighbors. Yeah? Divided by h squared. Well, let's say that I have, now I sample my points, right? So I think of f as a function on a line, yeah? And I want to find the derivative of f, assuming that I have the values f of x at these points. And we call the spacing h. But what is the derivative? Well, all I'm going to do is put a minus 2 here, a 1 there, and a 1 there, and that takes me from the value here to the second derivative here. Yeah? Does this make sense? Right, all I did was apply this formula. In particular, I can make a second derivative operator. So if I have a bunch of yks, then to get a bunch of y prime prime k's, at least the first order, I can just apply this formula all the way down the line. Now, I've left out one detail for you guys. Oops, I just drew this stencil there. Which is what happens at the boundary, right? Because over here, let's say I'm all the way on the left-hand side, I'll have a minus 2, a 1, and then a 1 beyond the left-hand side. Yeah? And that's exactly encoding the boundary conditions we were talking about before. Right? So for example, if I have Dirichlet boundary conditions, I might just say this number is 0, so I can ignore it. Yeah? Or if I have Neumann conditions, right, I might say f prime is 0. In other words, this thing equals that thing. So that means the 1 here really makes that guy into a 1. Or I could have periodic boundary conditions and just look over the other end. Right? So anyway, this gives me a way to take a function sampled at a bunch of points and give me back the second derivative. Yeah? Well, in fact, I can write this in a matrix. Right? So let's say that I took all of my y values, y1, y2, y3, y4, y5, and so on, and I just stuck them in a big pile of numbers. Right? Then to go from y to y prime prime, you can see, what do? I apply this thing where I take, a minus 2 at the center, 1, and 1. Right? If I stick this all into a matrix, I get this guy right here. This is a sparse positive definite matrix. Funny thing, huh? Because this is a discretization of an elliptic operator, the Laplacian. Yeah? So in fact, all this theory carries out exactly the same. In fact, you have Dirichlet conditions, remember that's kind of like sticking a 0 on the end. So in other words, you just truncate the one that was on the outer boundary of the matrix. Okay? If you have Neumann conditions, then you kind of move the positive 1 to this place, so that cancels with minus 2, you do minus 1. And if you have periodic boundary conditions, right, then your domain wraps around the left-hand side. Yeah? These are Laplacian matrices, right? So remember I told you that a derivative is to a function as a matrix is to a vector? Well, what did I just do? I discretized a function as a vector, and then when I discretized the derivative, I got a matrix. So in fact, this is how we're going to discretize PDE. We can do the same thing on a 2D grid. We'll stop in just a moment. Where let's say that I now have a function like this, right? And I differentiated him on a whole grid. Well, what is the Laplacian? Well, he's the sum of the second derivative in this direction and the second derivative in that direction. So in other words, I'm going to get a minus 4, 1, 1, 1, 1. Yeah? And I can still construct a sparse positive definite matrix out of that. Yeah? So in fact, when we solve PDEs, usually our very first step is to take all the derivatives and discretize them. And then we're just going to solve it like a big linear system of equations. Nothing so bad. Now we'll conclude with one note, which is, you should ask, well, Justin, why did you skip to the second derivative of f? Yeah? Well, the first derivative is a little tricky, right? Because the second derivative, you kind of naturally have a nice symmetric discretization at a point, right? But when we talk about the first derivative, usually we kind of look to the right and subtract it, right? But that would create something kind of asymmetric, right? So let's say that I took a right-hand derivative. Then I would need a boundary condition over here, but I wouldn't need a boundary condition over there. That's a very fishy story. Yeah? So there's something kind of weird about first derivatives. Maybe, we'll return to that on Wednesday's lecture, and then we'll go through at least one elliptic, parabolic, and hyperbolic PDE and solve it. In fact, how do you think we're going to solve elliptic PDE? Well, remember, we were solving things like Laplacian of f equals g. Well, now we can think of f and g as just vectors, right, of values on these grids, and this thing as just some matrix L. We're just going to solve it. Yeah? And so the state of the art for solving elliptic PDE discretely is called Conjugate Gradients, and it is exactly what we covered a couple weeks ago. Yeah? Okay, so we'll stop there. If somebody could hit the camera, that'd be great. And on Wednesday, we'll go over a couple example PDE, and then you'll never have to take this course again. Hopefully. All right.